Okay, so recording is going, so we can start the afternoon session. I am really very pleased to welcome, at least virtually, Enrico Le Donne from Freiburg. And he is going to talk about the sub-Riemannian viewpoint of Pfefferman extension theorem. So how do you know that, Enrico? So Enrico.
Okay, thanks. I'll start. Thank you. So thanks to the organizers. I'm really happy to talk at this conference together with some of my earliest teachers, such as Marco Abate and Anders Carlson, who actually they introduced me to this type of subjects. So as the title says, I'm going to have a discussion on a theorem which is quite well known by Pfefferman, but I will give a new viewpoint and in the context of sub-Riemannian geometry, hoping that you know extremely well what the Pfefferman theorem says, but maybe you do not know what sub-Riemannian geometry is. But okay, please stop me at any time if you have questions. Okay, so let's start just recalling what is the theorem I'm talking about. It says that every biholomorphism between smooth, strictly pseudo-convex domains extends smoothly between the boundaries. So this is what I mean. So let's suppose we have D1 and D2 domains in Cn that are, say, bounded, strictly pseudo-convex, and the boundary is smooth, so with smooth boundaries. And suppose you have F from D1 to D2, a biholomorphism. Then the map F extends to a map, let's call it boundary of F, from the boundary of D1 to the boundary of D2. And this extension, let's put it as two plane, and the boundary map is seen. Okay, so this is the statement. I'm not going to recall, at least not initially, was strictly pseudo-convex domain, even if probably all of you know it. Okay, so this is the theorem. And now let me immediately get to the punchline of my talk. So this is the message that I want to bring to this seminar, is that the map boundary of F is a map from D1, boundary of D1 to the boundary of D2. This is not only a smooth map, is a conformal map. Conformal map, not with respect to some Riemannian structure, but with respect to some sub-Riemannian structure. And as in particular, and therefore, this map is smooth. Okay, so and I would like you to see this these two claims as two different claims. So one is that the map is conformal, which I should explain you what I mean with that. And the second claim is that conformal maps are smooth. And actually, really, these two claims come from two different works that I did. The conformality was proved by together with Capogna. And then, do you still see my pen moving? No.
Yes. Yeah.
Okay. And instead, the other the fact that the conformal maps are smooth. This is a work that I did with Capogna, Citti, and Tartazzi. Okay. Let's move on. I think there is a problem. Do you see a new slide, an empty slide, or not?
No, we see the slide with the plus thing that you wrote is, and therefore it is still fit.
No. There's some problem. You see now? Okay. Okay, let's try it. Okay, so these are the messages about the maps. Okay, so first, let me first clarify the fact that how we can easily see that the boundary map exists. I mean, the map extends at least as a map on the boundary. And this is really something that is very linked with the program of this conference. So, because it comes from the hyperbolicity of the domains. So the existence of this boundary map follows from the theory of Gromov hyperbolic spaces. This is what I mean. So when we have, again, a bounded, strictly pseudo-convex domain with same assumption, with a smooth boundary, then we can equip the boundary, equip the domain with the Kobayashi distance, or also other distance like Bergman distance. Okay, so that becomes a metric space. And these distances, however they are defined, I'm not going to recall you, these are defined via the holomorphic maps on D, holomorphic functions on D. And therefore, they are preserved by B-holomorphisms. So B-holomorphisms are obviously isometries with respect to these distances. Okay. Now, the first important thing to remark is a result by Bonk and Ballock that they prove that strictly pseudo-convex domains equipped with these distances are Gromov hyperbolic. Okay, and moreover, actually, Gromov hyperbolic spaces have a notion of visual boundary equipped with the visual metrics, so I call it visual metric boundaries. So the boundary of this domain coincide with the topological boundary. Is it correct that you don't see what I wrote last?
There is some lag between your right and
Lag. Okay, maybe like this is better. Okay. All right. So then what do we know from the theory of Gromov hyperbolic spaces? So now what we have is that if F from D1 to D2, such domain is an isometry, for example, it is a holomorphic map, then this map continuously extend to a map from the visual boundaries and therefore the topological boundaries. And this map has also a metric property. This map is a quasi-conformal map. No. In particular, it's a homomorphism. Okay. So I will discuss. I will wait, but I will tell what's a quasi-conformal map with respect to this the visual distances. Okay. But this was the first message. Okay, the existence really comes from Gromov hyperbolic spaces. Okay. Now, before we continue, I really want to make a remark on the distances that we're putting in the boundary. Okay. The fact is this that so I want this to be a warning. So when we have these domains, as usual, bounded, strictly pseudo-convex, with a smooth boundary, equipped with the Kobayashi distance. Then this as a metric space, okay, may not be negatively curved. So we cannot think of like a Riemannian metric with negative section curvature. It's not, okay? And it's not even locally cut -1 space in the sense of metric space, okay? So we don't really have local negative curvature, not even in a metric sense, okay? But my message is that roughly near the boundary of the set, maybe let me say D is almost cut -1. And maybe you can even think that the D is almost like the complex hyperbolic space. So, I mean, this is a vague sentence. I will not make it more precise than this. So you have the boundary of D. What I'm saying that if you get close enough, then like small neighborhood really here behave, they have expansions for the distance that are similar to the one of the complex hyperbolic space. Okay. All right. So stop me if you have questions, or at least tell about it if you have questions. Okay. Now, before even remembering what is a quasi-conformal homomorphism, I would like to tell you that in the discussion that we're going to have, there will be several distances in the discussion, and I hope that you will not get confused. So there are several distances inside the domain and several distances on the boundary. Okay, let me tell you what are these distances that we are considering. Okay, so say the distance 0. Okay, let's start. So this is we already let's record this is the Kobayashi on D, or you can also take the Bergman distance. Okay. First distance is the visual function that I will recall soon. Visual function associated with Kobayashi. Then, and this will be a distance on the boundary. Then on the boundary, we are going to have a very special distance, and this is the sub-Riemannian distance. On D. And I hope that this talk will make you understand that this is really an important role of sub-Riemannian geometry in the theory of complex hyperbolic spaces. And then there will be a third distance we will discuss toward the end, that is the hyperbolic filling. This is something that one can do for any metric space, but we are going to consider the one associated to the sub-Riemannian distance. And this will be again a distance on the domain D, or maybe just on a tubular neighborhood of the boundary of the point. All right, so let's immediately clarify what is the visual function. And also, that's why I call it visual function, not visual distance. Okay, let's fix a base point. O inside D, so base point. And then for all points X and Y, now these are in the boundary, we define this visual function, rho of O between X and Y. This is the exponential of minus the Gromov product between X and Y, base of O. Okay. other people will recall in this conference, but for those that only watch this video, will recall what's the Gromov product between X and Y. So this is Gromov product based at O between X and Y. This is the limit. So you take sequence xi going to X, yi going to Y. These are elements, their sequences in D. And then what you do, you take 1/2 of the distance between xi(O) plus distance yi(O) minus the distance between xi, yi. Okay? Now, so this is the definition. Okay? Now, some remarks immediately. So, okay, in our setting, this will be a good definition. So if D is a cat minus 1 space, then really this function rho of O is really a distance. So it satisfies the triangle inequality. And this is by the work of Bourdon. Some authors call this function the Bourdon distance. So I will call it maybe the Bourdon function because it's, in our setting, it's not going to be a function. Okay. Now, if D is just delta hyperbolic, so hyperbolic, Gromov hyperbolic, then what we have is that rho of O is quasi-conformally equivalent to distance. And this is what we call a visual distance. So when you have a Gromov hyperbolic space, the visual distance is not uniquely defined. It's defined up to quasi-conformality. And therefore saying that the map is quasi-conformal does not depend on the choice of your quasi-conformal distance. Okay. So now this function, because it's not really a distance, okay, this function is in the same class of the visual distance. Okay. Now, whenever you have an isometry between hyperbolic space or even a quasi-isometry, then the boundary map is quasi-conformal with respect to these visual distances. With respect to the visual function. Okay? All right. So maybe at this point it's better that I clarify what I mean with quasi-conformal. Okay, what's a quasi-conformal map? Here's the definition. So first of all, there are many definitions in the literature for quasi-conformal maps. Now, in some nice settings, like the one we are going to have, sub-Riemannian manifold, these notions are going to be equivalent. Okay, so all the definition of quasi-conformality are the same. Here, I will present the metric definition because it's just easier to remember. But one should know that there are other definitions that one can use. So this is the definition. One consider a homomorphism between metric spaces, and then you say that it's H quasi-conformal if one does the following. For any X, one take the ball of radius R, maps it via F. Now this is going to be a neighborhood of the point f of X. And therefore one can put inside a ball, and let's consider the largest ball is going to have, by definition, radius little l. And this blob is going to be inside a ball. It's called the shortest and the smallest radius, capital L. Okay, so we have two quantities. Now we take the ratio and we take the limit when R goes to 0. If this number, lim sup in general may not exist, maybe the limit, lim sup is bounded by H, we say that the map is H quasi-conformal. Okay, so also pay attention that maybe this quantity is not really behaving like R. Okay, I'm not saying that the lim sup between this and R has a limit the same with this, and then the quotient is bounded by H. Okay. Even if, in our case, this is going to be the case. Really, this will behave like R with a number, this is behaving like beta R. And then the ratio is going to be bounded by alpha over beta. Okay. And one thing is that this quantity here is going to be important. We're going to call this quantity the distortion at x of the map F. Okay. Okay. Now let's clarify when let's see some example when a map is quasi-conformal. So these are some remarks. Okay. The first remark I want to make is that if you have two distances, d1, d2, they're distances on the same set. Like, for example, the distance that we are considering on the boundary of our domains. Now, if we know that for all x in the set, there exists the limit between of the the ratio of the two distances when y goes to x, and I'm not saying that this limit is bounded uniformly. I'm saying just this limit exists. Then d1 and d2 are one quasi-conformal. And I will clarify this because it's going to be important in my discussion. So you see, what this property is saying that, okay, so infinitesimally the ratio is independent on how y goes to x. And it's fine. Okay, this exists this limit. And therefore what happens is that you know that infinitesimally a ball with respect to d1 is going to be a ball with respect to d2, maybe of a different radius. But this means that if you look at the identity and now you compare the two distances, when you put ball inside a ball, then the radius is the same and the ratio that it counts. So this is what, so this sentence means the identity map seen on the source with the distance d1 and the target with distance d2 is a one quasi-conformal map. Okay. All right. Now, similarly, if now we have a map between spaces that are maybe more structured than metric space, and let's say that this is the map is differentiable in some sense. And you know that the differentials, without specifying what it means, and the differentials are dilations, then F is one quasi-conformal. And this it's the analog of this fact here, right? So it means that the map is stretching, but every direction is stretching the same way because the differentials are dilations. Okay, and therefore the map is a one quasi-conformal map. Why I'm stressing this fact? Because when we have a sub-Riemannian manifold, then every quasi-conformal map, not necessarily one quasi-conformal, every one quasi-conformal maps are okay, almost everywhere, in some intrinsic sense, differentiable. So really, like in the sub-Riemannian setting, quasi-conformal maps are not too wild. Okay. Okay. So this was the remark on quasi-conformal maps. Now, at this point, I want to spend some words on the definition of sub-Riemann structure on on the boundary of strictly pseudo-convex domain. Okay. Other questions? Marco, please check for questions.
No question yet. You can go.
Okay. I don't hear anything, so I go on. Okay, so let's go back to our setting. So we had bounded, okay, strictly pseudo-convex. Domain in ECN with smooth boundary. Now, okay, first thing, the boundary is a manifold. Okay, this is what means smooth boundary. Okay, so we have a manifold. Now, on this manifold, there exists a contact structure or a contact distribution. Okay, let me tell you what it is, and then it's clear that this is a distribution, at least. So, what is the distribution? The distribution is a subset of the tangent space of this manifold. Okay, and at P is defined like this: is the maximal complex subspace. So this N was P, on a subspace of the tangent. Okay, so this is a codimension 1 subspace inside Cn, so it's definitely not a complex space, but there exists a complex maximum complex subspace. Actually, it's the same of saying is this intersect with I times TP. Okay, so this is how you define this subset of the tangent. Okay, now part of the assumption that we have a strictly pseudo-convex domain is that this distribution is bracket generating. So Lie brackets generates the missing direction. Okay. Now, moreover, on this subspace, on this distribution delta, there exists a positive definite metric tensor, which is the Levy form. I'm not sure if I have to recall the Levy form, but I decide to recall what it is. Hope this crowd, somebody in the crowd does not know. So okay, let's say that. So we can take the function that is the sine distance function from the boundary. So this thing is near the boundary, feel smooth, okay? And so the boundary is exactly the pre-image of 0, and I said that D, we take the convention that F D is the pre-image of the positive numbers. Okay. Now, so for all point P in the boundary, and for all vectors in Cn, but we are seeing this as the tangent in Cn, we define the Levy form. The Levy form associated with phi is defined as the sum of the indices alpha and beta from 1 to n, the second derivative, that is the alpha and the beta of phi evaluated at p, x alpha, x beta bar. Okay, so this is the definition of the Levy form. Now, asking that a domain is a strict pseudo-convex domain, really by definition, one of the equivalent definition is that this form is positively defined. On that. Okay, so now what we have, let's recall what we have by the assumption of strictly pseudo-convex domain. We have a manifold on which we have a bracket generating distribution, on which we have a metric, positively defined metric tensor. Now, by definition, we have that this triple delta, the boundary of D, delta, and Levy form, this is a sub-Riemannian structure. Okay. So a sub-Riemannian structure is like a Riemannian structure, but together with the choice of a sub-bundle of the tangent bundle. Okay. But likewise, like in Riemannian geometry, one has an associated distance. Let's call it a sub-Riemannian distance is defined as follows. The distance, so the sub-Riemannian distance between 2 points P and Q, this is the infimum of the length. This is with respect to the Levy form LP of gamma, where gamma is an absolutely continuous curve connecting P to Q, with the extra assumption the derivative of gamma is almost everywhere in the distribution method. Okay? So the general theory of sub-Riemannian geometry tells you that because the space, because the distribution is bracket generating, this distance is finite. On connected components of the manifold is finite, and really induce the same topology. Okay. Now, what has to do with this sub-Riemannian distance with the visual distance of our Kobayashi distance? This is one of the key facts proved by Balog and Bonk. What we have is that what they prove is that the sub-Riemannian distance is quasi-conformal, quasi-conformally equivalent, I should write. Conformal to the visual distance with respect to some base point. Okay. Okay. And therefore, we could say that our boundary map is a quasi-conformal map with respect to the sub-Riemannian geometry. However, let's pay attention because there are many non-smooth maps from these two sub-Riemannian manifolds that are quasi-conformal. Okay. So saying that you have a map that's quasi-conformal between two sub-Riemannian manifolds, this is really not a strong condition. Okay? But maybe at this point, I would like you to have as a side question the assumption of what happened if G is an isometry. Okay. Now, being an isometry really depends on your choice of the distance. If you change the distance with a quasi-conformal equivalent distance, the map may not be an isometry. Okay. But still, like, being an isometry is a very strong assumption. And maybe at this point, we can also see that our boundary map can be seen as an isometry. Here's a small note. With respect to boundary distance, visual distance is rho O and rho F of O, then this boundary map is an isometry. Okay. Because it was an isometry between two metric spaces. If you consider now the image of the base point, then everything is preserved, and therefore the map that it induces is an isometry. Okay. However, of course, this function rho 0 is not very regular. It's not even a distance, okay, but not to have the triangle inequality. So maybe we cannot expect any regularity for just preserving some visual distance. Okay. On the other hand, if you say that the boundary map is an isometry with respect to the Sub-Riemannian distances, then this is a strong statement. Assumption statement. All right, let's put assumption. And like in Riemannian geometry, this actually implies that the map is smooth. Remember, there is this Meyer-Vietoris theorem. Okay, don't remember, sorry. So there is this well-known theorem in Riemannian geometry. If you have a distance-preserving map, homomorphism, between two Riemannian manifolds, then the function is smooth. Okay. Now, in sub-Riemannian geometry, one needs to give a proof, maybe quite different from the classical one, but it's still true. Okay. So if you happen to know that this map is an isometry with respect to the sub-Riemannian distance, then you still have that the map is smooth. Okay. So now we have to play with these two things, that we know that the map is an isometry between these functions, and we would like to get that this is a sub-Riemannian isometry. Of course, this might not be true, but the correct analog for isometry here is to put a one quasi-conformal map. Okay? But now what we have to understand is how to link this visual function with the sub-Riemannian distance, because by Balog and Bonk, we only know that they're quasi-conformal equivalent. And now what I'm going to say next is a stronger claim than the one that Balog and Bonk proved. So this is the crucial fact. As I said, this is together with Capogna. So if we consider the visual function and the sub-Riemannian distance, so remember, these are two distances in the boundary of strictly pseudo-convex domain. I'm claiming that they are pointwise, asymptotically, one plus epsilon quasi-conformally equivalent. Okay, well, what do I mean is the following. If you take any point in the domain, in the boundary, and you fix any error epsilon that you want, then there exists some O. There exists some, you need to allow yourself to change the base point in such a way that the identity from the space with the visual function, the space with the sub-Riemannian distance, this map has distortion at x less than 1 plus epsilon. And actually, it's a stronger statement. What I'm going to say is that for any x you take, and for any circle you take here, then if you take the base point close enough to x, then the near x, the two functions really behaves actually 1 plus epsilon by Lipschitz. Okay? So in particular, the distortion is close to 1 as you want. Okay, so this is the big claim, and let me modulo this claim. Let me try to tell you then how you conclude that the map is the boundary map is 1 quasi-conformal. Okay, how does one prove the quasi-conformality? Like this. So let's recall. So we have a biolomorphism between two domains, strictly pseudo-convex. We equip them with the Kobayashi distance, and then this map is just an example of an isometry. Okay. Now, this isometry induces a map on the boundaries. And notice that now the map, we have the map between the domains, but now we are going to see this map differently, changing the distance on the domains. But the map is always the same source, same target, same law. Okay. Now, if we consider whatever O we take, in the image we take rho of f of O, then this map is an isometry. Okay, so the map is induced by Gromov hyperbolic space theory. Okay, and it's obviously an isometry. All right. Now these spaces here, now we can see them as so what happens if now we change the distance and we take the sub-Riemann distance? Now, if you change, if you fix a point in the boundary and then you choose O close enough to f of this point, to this point, then you know that you can make these two distances 1 plus epsilon quasi-conformal. Okay? And likewise in the target. Okay? But notice that the map is always the same, is the map. And now this map here does not depend on the choice of O. The distance is always the same, it's a sub-Riemann distance. So what you have is that this map is a 1 plus epsilon, okay, square quasi-conformal map, but for all epsilon. But the map is always the same, and the distances are always the same, and therefore the map is 1 quasi-conformal. Okay. Now, this is how you get to the metric condition of the map being quasi-conformal with constant 1. Okay. Next, what we have to understand is how to improve this as to say that the map is smooth. Okay. This could be like a second story, but let me ask how many minutes I have more, so I can ponder.
We have 8 minutes.
8. Okay. Maybe I will still say something about why this is true. Okay, here I have a choice. I can explain more about this, or explain why you have the one quantity why you have smoothness here. So the second part, maybe I'll squeeze it at the end if there is time or interest. This now becomes something that is really like geometric analysis on sub-Riemannian manifold. Okay, now has nothing to do with complex geometry, and is really a problem in that can be solved using PDE theory, because I'll make it brief and then maybe I'll go back at the end. Now, when you have a sub-Riemannian manifold, or two manifolds, and you have one quasi-conformal map, then this map preserves the solution of the Q Laplacian, the horizontal Laplacian, the Laplacian with respect to the distribution. This becomes a partial differential equation. And now saying that a map has a morphism property with respect to some operator, this most of the time give you some regularity of the map. The main idea would be still think at the beginning, think of isometries. If you have an isometry, isometric map, then this must send harmonic functions to harmonic functions. Okay? Since also in sub-Riemannian geometry, harmonic functions are smooth. This is by the Riemann theory. Then what we have is that the map is sending some special smooth function to other smooth functions, and one can expect that this gives you smoothness of them. Okay, so but I will not say some more about this because this is really a PD problem. Let's talk more about why this we have this quasi-conformality, and this is how it comes in the play. I mean, these are distances in the space, is in the boundary, but it would be nice to work back on the domain. Okay, and this is what is what we call the hyperbolic filling of the boundary. Okay, so the idea is the following. This is also can be done for all metric space. We have a metric space Z, and now what we want to do, we want to consider the product with R or R plus, and make a bigger space that is hyperbolic, Gromov hyperbolic, in such a way that the visual boundary is going to be Z. Okay, so what we want to do, we want to do the opposite of taking the visual boundary, the opposite of okay. And this was done by Bonk and Schramm. So the function will be called Bonk-Schramm filling metric. Okay, now I will, so the theory is much more general, it's for metric spaces, but I will immediately adapt in our context. Okay, so we have our domain D, and now let's call H like the square root of the distance from the boundary. Okay, actually I'm not really sure if, okay, there might be a typo that, yeah, I don't have to put the square root because you already put the square root, but okay, the distance from the boundary. Okay, and now close to the boundary. So remember, this is a smooth manifold. So we really have a tubular neighborhood theorem. So you can project on the boundary. This is the projection. And now you define this metric here. So this is going to be a function that is defined in a neighborhood of the boundary. So we have a boundary. Okay. Then in a neighborhood, we have a well-defined projection that is smooth. Okay, and now what you do to me, so now you will define the distance between 2 points here as a function of the distance of the points from the boundary and the sub-Riemannian distance on the boundary. Okay, and here C. Okay, CC is sub-Riemannian. Okay, sub-Riemannian, also called Carnot-Karateoder. Okay, so as a function of the sub-Riemannian distance on the boundary, of the projections of the points on the boundary, and the distance from the boundary, which is the maximum, okay, we define this function here. Okay, let's call it the Bonk-Schramm filling metric. Now, what is true is that this distance, this function, really defines a distance in the neighborhood, in a small enough neighborhood of the boundary, and this is really 1C quasi-isometric to the Bergman or Kobayashi distance. Okay. And therefore, this is the result of Balog and Bonk, but we actually have to upgrade. Okay, so we prove something stronger than this one. Of course, like when you have two distances that are quasi-isometric, then one can easily prove that the the visual distances are not only quasi-conformal, but they are really Lipschitz equivalent. Okay, I will skip I wrote a proof of this consequence, but I will skip it. Okay, let me just note one small thing that in this formula, right? You can really easily prove, and this is actually was done also by Monk and Schramm in a greater generality. It's really a metric calculation to prove that these two distances are conformally equivalent. And the proof is very elementary, easy. I can write it here. I mean, what you have to do, you write the definitions, and then you will get that the ratio, just play with the exponential and log, okay? So you get that the limit of these two distances is a number that does not depend on the point q, on how q goes to p, okay? As the exercise I did at the beginning, since this ratio exists, these two functions, these two distances are one quasi-conformal, okay? So to say, okay, these two distances we can consider as the same because they're in the same conformal class. The stronger fact is instead relating with the sub-Riemannian distance, okay? Sorry, relating the filling with the Kobayashi distance. So why they are one quasi-isometric was coming from this big estimate that Bonk and Ballo proved, okay? Maybe I will skip these details, but one has to go back and upgrade this estimate. And what one can prove is the following. I will soon finish, okay? Now, we cannot prove something global, but what we can prove is something infinitesimally, like on a small scale. And this is how you relate. So you have the boundary, you have a point, P bar. Now, if you fix an error epsilon, then there exists some ball, the ball in the sense of Euclidean ball. Now, that whenever you take another point Q in this ball, then if you take points now in, so this was Q, this was X, and this is Y. Now, see, should be, you should understand that this is really close enough to P bar and close enough to points where you have the control, P and Q. Now the distance, the two distances, the Kobayashi distance and the filling, they are 1 plus epsilon quasi-isometric. So I'm sorry, yeah, 1 plus epsilon quasi-isometric. This is really the hardcore of my result with the Capone. Once one proved this, and this is really like redoing Balog and Bonk and using a lot of their ideas, then one get that these two distances are Lipschitz, 1 plus epsilon Lipschitz at small scale. Now I will reconclude again and then finish. Now, this is again the theorem, right? So you have the isometry inside, gets an isometry inside for the visual distances, which are actually Lipschitz equivalent to the Gromov filling, Bonk and Schramm filling, which is conformally equivalent to the sub-Riemannian distance. And therefore, this map is a 1 plus epsilon quasi-conformal map for any epsilon, and therefore it's quasi-conformal. Okay, maybe just to finish, let me also point out how I like this viewpoint, because I like that we are mixing 3 different types of mathematics, because here there is complex analysis. Okay, remember we were starting from a biolomorphism. All of these maps, this is really a metric geometry discussion, and at the end what we had was a problem in sub-Riemannian geometry, which to upgrade to prove that this map is smooth, you really have to do some geometric analysis. I really like that we're mixing 3 types of subjects in mathematics. And with this, I just thank you all for the attention.
Thank you. Other questions or not comments? Good.
Yeah, I have a question. There are some refinements of the different theory in case of the boundaries are not infinity, that's CK. And there is extension of hypermorphism to CK minus 1 minus epsilon.
Okay, I will need someone to repeat the question because I'm not hearing much.
Okay, coming up.
Yes, I have a question. There are some refinements of the Pfefferman theorem in case the boundary is not of class infinity, but of class CK. And there is extension up to some regularity. There is a regular extension. Can your approach have such a quantitative version?
I guess so. So let me see. So okay, as always, when I work on this, I start first with the case of isometries because it's the more rigid, and if I cannot solve that one, I cannot even solve more difficult problems. So if we have if you can prove that the map is an isometry between subriemannian manifolds of regularity CK, can we prove that map is CK? Yes, this is still true. Because when you write the sublaplacian, and then it's going to be an operator with CK regularity, so that's okay. Now, yes, my answer should be yes. Is yes. Of course, like, I didn't do all the calculation in that setting. But I feel that like if the regularity of the boundary is CK, then you get that the map is still a conformal map that is between manifolds of regular CK, and this is a CK diffeomorphism. Then there was, I think, some other question in the sense like some other variation, but that I didn't get that. So one was the regularity of the boundary, and
in case the boundaries are of class CK, I think you get extension CK minus 1 minus epsilon. There is a little loss.
Yeah, dimension 1 is CK minus
of course, yes. There is always the like, yeah, because we are in a step 2 manifold, so probably yes, isometry. It could be that you don't get to the final point, final case. So you have regularity of CK minus 1. This is what you're saying, yeah.
So almost minus 1, depending on if it's an integer or not. Okay, thank you.
Thanks.
I'm a learner in this subject, but I knew the work of Barok and Bonk, and I read
Closer to the microphone, please.
Otherwise, the microphone.
It's there.
Okay. So I'm aware of the work of Barok and Bonk. I see the difference that what you bring, but I'm confused with what Léa Blanc-Santi did about the subject, because we found the same construction, and so if somebody can clarify for the beginner I am, what's exactly what brings Léa Blanc-Santi, what brings.
So you want to know the difference between the work of Ballon and Bonk and who?
Léa Blanc-Santi did something there.
Léa.
I don't think exactly the supremacy. There are a lot.
Léa Blanc-Santi.
Okay.
You didn't decide.
Léa Blanc-Santi.
I don't know. I'm probably not able to answer to this.
The other something consider is the generalization of Ballon in the case, in a special case, in almost complex manifold.
It's what's the it looks like it's some kind of assumption of the body.
The generalization.
Yeah.
Yes, I mean, I admit that I don't know very well the literature of pseudo-convex domains, so I I start learning from I mean, the relation that they have of Gromov with the Gromov hyperbolic space with the two papers of Ballung and Bonk. I don't know if before then somebody else proved that strictly pseudo-convex domains are Gromov hyperbolic. But definitely the idea of doing this hyperbolic filling, this came with the work of Schramm.
The uncertainty generalized in the case of regions in a normal complex manner. The work is the one really the one by Gromov.
Okay. So Enrico, first of all, thank you very much for the very nice talk. So the question I have is the following. You can define this sub-Riemannian metric in case you have a bracket generating distribution, which I think is the case if the domain is the so-called confinite type. So dimension 2 should be the same as the Angelo type, if I remember correctly. And well, in that case, you have also the Gromov hyperbolicity and equivalence between Gromov boundary and boundary of the domain, let's say in C2 with pseudo-convex domain of finite type. So do you think you can repeat in that case?
Sorry, if you interrupt. So the discussion is to remove the assumption that is a strictly pseudo-convex?
Yes, and to replace with finite type, let's say confinite type where you have a bracket generating distribution. So that you can define this sub-Riemannian metric by Sussman theorem and so on, right?
Yeah, this I don't know. Of course, like one needs the distribution to be bracket generating because otherwise the distance is not going to be finite. But as soon as it's bracket generating, then you have local accessibility. But you still also have to have a strictly positive Levy form, because otherwise how do you measure length? I mean, the length should be positive for non-trivial curves.
Okay.
So for this, I do not know how to go beyond the strictly pseudo-convex assumption. And maybe I mean, there is always the assumption of boundedness. This I don't know if, I mean, probably one can remove this assumption, even unbounded. Okay, the visual boundary might be bigger because there are other points except the topological boundary. But then, so I do not know how to remove the strict convexity.
So essentially, you want to replace the Carnot-Caratadori metric with the Levy form with some other metric which is well defined there and relates to the complex geometry. So maybe the Catlin.
Yeah.
Matteo used. Okay. Thank you.
Thank you all. Thanks for the questions.
Somebody else has questions? So the last one, apropos of changing the metric. You sometimes use the Berman metric in the domain, sometimes you use the Kobayashi metric, Kobayashi actual distance, Berman distance. Do you think you can have a characterization of the kind of invariant distances that can be used for this kind of argument? Because there are other invariant distances on defining these domains that in principle might be useful.
So let me say that what's really important of the Kobayashi Bergman distance is this estimate here. And actually, like all distance, like Kobayashi distance and the inner Karateodori distances, they have this expansion. Right? And whenever you have this expansion, then you get the distance that you have is asymptotically, infinitesimally conformal to the sub-Riemannian distance. So this is what I can say. But I don't know if there is one that is more canonical than the other. Of course, now if you look enough of this formula, what you really see is that if you remove the errors, right, what you get is exactly what you get for complex hyperbolic space. That's why what I was saying, that in some sense, near the boundary, the distance is like the one of the complex hyperbolic space. But this is also, I mean, this is also geometrically expected because, I mean, you can really put a tangent ball in your bound. So you have the boundary. You can put a ball, and then really the first expansion of the Kobayashi distance should be the one of the complex hyperbolic space. Right? And what did I want to say? Yeah. So, but I don't know if there is one is more canonical than the other inside. To me, outside, I mean, on the boundary, it seems that sub-Riemannian geometry is very, it's the best one.
Okay, thank you. Yes.
Just point out that it's possible to cancel this section.
Can you repeat, or someone else closer can repeat?
It is saying that it is possible to take care of the epsilon, I understand correctly. So it's possible to get better estimates for the, I think, for Kobayashi, right?
For Bergman, the same more.
And also for Bergman.
Better estimate than these ones?
Yeah, apparently,
I
yes.
mean, I would say that this is.
I mean, it's it's good for you, but it doesn't change anything what you said.
Okay, maybe let's. Okay, maybe one can have a better estimate because our statement is not really implying the Ballon and Bonk estimate, because you see, Ballon and Bonk say that what is it that they say? They say that these two functions are by Lipschitz equivalent on the boundary. So near the boundary, these two are by Lipschitz equivalent. And instead, I mean, no, because you're saying that inside these are 1 plus epsilon twice isometric.
Well, there is some.
No, that's okay. No.
There is
This is only local statement, but this is saying that they are 1 plus epsilon twice isometric. Instead, Balogun-Bonk said that globally, in the sense of in the whole neighborhood of the boundary, they are 1 plus c twice isometric. So these are two statements that.
This something seen no Ballon, the Ballon, there is big seen no epsilon.
Yeah, that's it.
Well, this is one typical thing that if we were everybody here at this point, I would say, then we can continue the discussion after coffee break.
Yeah, I'm sorry that I could not be there.
By the way, this paper is already on the record.
Yes, it has been published in Mathematical Now.
Thank you.
I mean, I'll be here if someone wants to chat. I'll be here tomorrow. We can chat more. I'll be happy to.
So you will be connected also later if somebody else wants to have a private conversation.
Yeah.
Okay. So let's thank Enrico again.
Thank you.
And